Good day, everyone. Today, our group would like to present our project, the design and development of a low-cost, energy-efficient radio broadcast receiver for disaster-resilient infrastructure. Our project is motivated by the fact that when calamities hit, power lines and cell towers often break, leaving people with no way to communicate. We are proposing a solution for this by creating an affordable and buildable radio to ensure that communities can still get the life-saving information that they need, even with no power. Our project was developed in line with the Sustainable Development Goals and core Ateneo values to promote resilient disaster preparedness. Specifically, we target SDG 9, 11, and 13, as well as the values of career personalis, being men and women for others, and exercising rootedness and leadership. To ensure the radio performs well, we applied key concepts from our major courses such as AC analysis, network theory, BJT analysis, and power optimization.
For our methodology, the project was completed in two phases. In the first phase, we developed an Arduino-based radio receiver using the TEA5767 FM module. In the second phase, we implemented the amplifier and speaker subsystem. Next. For our radio receiver's display, we used multiplexing to control all 4 digits efficiently. A 74HC595 shift register handles the segment signals, while transistors are used to activate each digit during the switching process. For the controls, push buttons are used to increase or decrease the frequency in fixed steps. The Arduino reads these inputs and sends the corresponding tuning commands to the TEA5767 FM module using I2C communication, where it acts as the master and transmits data through the SDA and SCL lines. That's it for our radio receiver.
For the speaker subsystem, it consists of an amplifier with 4 stages, 2 voltage divider amplifiers, and 2 emitter follower stages using 2N3904, TIP31C, and TIP32B. The speaker was constructed from scratch paper, neodymium magnets, 0.1mm copper wire, and tape. The wire was coiled around the magnets, and the diaphragm and springs were made of paper.
For the results and discussion, we evaluated the system in terms of signal strength and power efficiency. Signal strength was measured using the RSSI from the FM module processed by the Arduino Uno, and the values were shown on 0 to 15 scale. The other testing showed that signal strength decreased with distance, dropping from strong to moderate levels. For indoor testing, signals were consistently on moderate levels. And now for power efficiency testing, the radio receiver consumed around 388 milliwatts, similar in both manual tuning and auto scan modes, while the speaker subsystem consumed around 222 milliwatts. Despite this, the total system power was only 39% lower than a typical 1 wattage commercial portable radio. The prototype has strong potential as an energy-efficient emergency device.
Testing was performed in 2 environments, indoors and outdoors. For inside testing conditions, it was conducted in the Ateneo University dormitories, where the system recorded the RSSI readings to show how strong the signal is for the following frequencies in megahertz. For outdoor conditions, this was conducted in Fowler Hall, 3rd floor, where the receiver signal strength was compared at an initial reference point to different distances of 1 meter intervals from 0 meters, 1 meters, 2, and 3 meters.
For the power efficiency, we connected the multimeter and ammeter settings in series before the battery to measure the current drawn by radio receiver when auto-scanning and when manual tuning, as well as the current drawn by speaker amplifier. The following are our demonstrations.
In conclusion, the study successfully demonstrated the design and implementation of a low-cost and reproducible FM radio receiver. The radio is energy efficient, operates at moderate to strong signal receptions, and can be a practical tool for emergency communication and preparedness. Moving on.
And finally, we recommend several improvements to enhance this prototype, such as refining the antenna design, upgrading the DIY subspeaker system, and exploring more compact weather-resistant housing for better field durability. The development of this project was supported by these references. Thank you all for listening.
I'm Sana, and I assume the position of a leader in this project, here to present my individual contributions as seen in our Gantt chart. From April 24 to 25, I actively participated in the brainstorming phase, which consisted of 2 Zoom meetings where we finalized the concept and overall system flow for our radio. This helped align our design direction and identify necessary components. On April 26, I worked in the virtual breadboarding using FritzLink, where I translated our initial ideas into a functional radio receiver circuit layout to verify connections early on. On April 27, I handled the introduction and, more importantly, the schematic drawing of the radio receiver and also finalized needed materials, which serve as the foundation for our design. This provided a clear and reliable starting point, ensuring that each component was corrected and logically structured before moving into further development. From April 29 to May 1, I focused on designing the radio receiver and connecting the physical prototype in the laboratory. Finally, I conducted individual testing on May 2 to 3, ultimately making the receiver work. This involved identifying issues, correcting connections, and improving overall circuit reliability. In May 5, I also tested with my group to validate the integrated system and further optimize its performance.